Ready, Alan?
Ready?
All right. Thank you, everybody, for coming. It is my pleasure to introduce Alan Pearl, who's going to defend his thesis today. He's been here 6 years. 6 years. And I think the most unique thing about Alan is that he was able to manage a strange situation in which he had 3 supervisors. Most people only have 1. And was able to somehow figure out how to design projects that brought in the interests of each individual supervisor. And I think that's a really unique skill. And everything was fun. And I feel like since there were 3 supervisors and Alan was so independent that I barely even did anything. Just say, oh, that looks okay. Actually, before I finish the introduction, I should have said this first. After the defense, we will have the real questions. So all of you will have to leave. Usually that does not take very long. Probably half an hour-ish. We will convene in the lounge on the 3rd floor where the graduate student offices are. Maybe some of you who are locals can help escort people who are not locals up to where we will be. And we will meet there and have a short toast to congratulate Alan for a job, hopefully well done. But now with that, I'll hand it over to Alan and take it away.
Thank you. Hey everyone, thanks for everyone coming out to my thesis defense. I'm blown away at how many people came out. It's pretty crazy. Yeah, both in person and on the Zoom call. Thank you for calling in. Yeah, thanks for the support. It means a lot. And anyways, I'm excited just to share what I've been up to here at Pitt for the past 5 or 6 years. Did we get a question on the chat?
You're recording right now.
Yes. Yeah. So yeah, the outline of my talk is as follows. I'll start by taking a step back and explaining some of the scientific background behind cosmology, galaxy formation, and the galaxy halo connection. The core of my talk is going to be showing off my 2 primary thesis projects, which are called Climber and Galtab. And finally, I'll conclude with the main takeaways of my thesis and give you a quick glimpse into some of my future directions too. All right, so I'm going to start by showing probably one of the most famous images in the history of astronomy. This is the Hubble Deep Field. This image is taken by the Hubble Space Telescope in 1995, coincidentally the year I was born. Sorry if that makes you feel old. Bad start. The story behind this image is that NASA decided to point Hubble at the darkest, emptiest region in the sky that they could find. And so they pointed at the spot for 10 straight days with Hubble, which was the best, most expensive to use telescope at the time, since this was 30 years before James Webb, which actually recently took a similar image of this field, or an even better image in under a day. But anyways, at the time, they pointed it for 10 days with Hubble, and no one had ever taken such a deep image, so no one really knew what to expect. You know, maybe there would just be nothing out there at all. But here's what they got. And it was probably pretty incredible. You'd never seen this before. I mean, it just seems like this endless expanse of galaxies of all sorts of colors, shapes, and sizes. And this was our first image, I think, that showed off the vastness of our universe. And for scientists at the time, I'm sure they're just like, you know, blown away at all of the wealth of data that's in here, and just thinking all of the clues that, because this tells us about the distant past, right? These galaxies are so far away that the light that we're seeing was emitted billions of years ago, right? Before it actually arrived here on Earth. And when the universe at that time was much, much younger than it is today. And so I guess the main thing I'm trying to get you to take out of this image is that these observations of distant galaxies contain clues about the past. And my job as an astronomer is to decipher these clues. So, cosmology. This is the study of how the universe has evolved and came to be the way that it is today. For example, from a variety of measurements, we figured out the relative size of our universe as a function of time. At first, the universe was infinitesimally small, at least in comparison to its size today, but then it suddenly started to expand rapidly. We call this the Big Bang. And as expected, the rate of expansion slowed down over time a little bit due to gravitational attraction of matter, but surprisingly, it didn't collapse back in on itself. This is because starting only roughly 4 billion years ago, another force, a mysterious force, we still don't really understand it completely, overcame the gravitational attraction and started to accelerate the universe back up. So you see at the end, it's starting to go concave up again. And nowadays, we've measured this entire expansion history from a variety of observations, and it's taught us pretty precisely what the universe is made of. So this recent acceleration was produced by some form of energy. We don't know what it is, but we call it dark energy. We know, though, that it has to make up about 70% of this cosmic pie chart here, which portrays the energy budget of the universe today. And the remaining 30% of the pie chart is almost entirely forms of matter, which we categorize into two main types. Ordinary matter, this is the kind we're able to see and touch. It's what we're made out of, it's what galaxies are made out of. And all of that, everything that we know essentially, it just makes up this 5% yellow sliver on the cosmic pie chart. Most of the matter is in the form of some unknown substance, totally invisible to us. And the only way we even know it's there is from the force of its gravitational attraction. And we call this dark matter. This brings me to dark matter simulations, aka gravity-only simulations. Simulations like this one being shown demonstrate how the matter distribution in the universe would evolve through the mutual gravitational attraction that it feels. But it ignores all other forces like the electromagnetic force, which is a good approximation for very large scales like this. In the video, you can see how the densest clumps of matter get even denser and more massive by merging and accreting the surrounding material. Each of these round structures that you can see represent a lot of gravitationally bound dark matter particles. And we call these round clumps halos. And unfortunately, we can't directly see halos like this on the left in observations, since dark matter doesn't emit light or really interact with light much in any way for that matter. But you can see galaxies, and halos are the only place where ordinary matter is dense enough to collapse and form a galaxy. So these simulations of halos can kind of tell us something about the spatial distribution of where galaxies should be. That is where they're typically located with respect to one another. We just need to figure out what kind of a galaxy forms in each of these halos. And this is called the galaxy-halo connection. So how do we formulate the galaxy-halo connection? Well, the most straightforward theoretical approach would be to use our understanding of physics and simulate everything from first principles, because we think that we understand physics pretty well, right? And broadly, we know what this should look like, I guess. We know galaxies kind of start out as very dispersed gas clouds of hydrogen that pretty closely follow the same distribution as dark matter on large scales. But when they get dense enough, they suddenly quickly gravitationally collapse, thanks to the fact that they can radiate away energy, kinetic energy, in the form of light. So gas clouds can go from basically the size of an entire galaxy, or even bigger, down to eventually smaller than a parsec, and that's how stars are formed. Stars add a lot of complication to this because they're comparatively really tiny, but they inject a lot of energy in the form of light back into the gas during their lifetime. And sometimes they just get up one day and decide to go into supernova, like the gas cloud picture right there is a supernova remnant. So yeah, to properly simulate the stars, the larger gas clouds, galaxies, and then the large scale environment of galaxies, aka the cosmic web, we have to worry about roughly 15 orders of magnitude, right? From 10 to the minus 7 parsecs all the way up to 10 to the 8 parsecs in distant scales. And don't even get me started on the different time scales that these processes take. This is a computational nightmare to try to simulate all of this. It's not possible. Although I will say, using some approximations, there's starting to be some impressive hydrodynamic simulations available today, like Choya, which was made by a professor here at Pitt, Evan Schneider, and her grad students, some of whom are here. And it's really great for high-resolution zoom-in analyses of galaxy formation. Or on the right, something like illustrious TNG, which is way bigger, and that's good for cosmological analyses, but it has to make more approximations. So that's the trade-off. All these types of simulations are still ongoing efforts. They aren't perfect. But one way to improve them is by feeding them in the galaxy halo connection that we need to produce. And we can learn about the galaxy halo connection from less physically motivated methods. So the other approach, which is more what I do, is the empirical approach, which relies directly on observations of the galaxy population, like this map on the right, the Sloan Digital Sky Survey. And then we formulate a logical way of placing these galaxies, which we can literally see where they are, into halos, which we're very good at simulating. Yeah, that's kind of how the galaxy halo connection work. I want to point out that you can see kind of similar cosmic web structures, both in the galaxy data and in the simulated structure. So this is a good sign that galaxies really do trace the same stuff that we're simulating. Yeah, so in practice, we just formulate the galaxy halo connection with some assumed correlation between the halo mass and some observable property like the mass or the brightness of the galaxies. Now I'll give you a cartoon version of what our current understanding is of the galaxy halo connection. Let's pretend that I've taken every single halo inside of a simulation, a largest volume simulation, and then line them up by their mass. Lowest mass on the left, highest on the right. And if galaxy mass correlates with halo mass, then we can paint in the galaxies with a similar mass trend. Okay. And this is a pretty good correlation, but it's not perfect. I've intentionally made it so that you'll occasionally see a more massive galaxy, which I've made bigger in the picture, living in a less massive halo. And yeah, but occasionally halos can host multiple galaxies. These are just the central galaxies in the halo. This happens if a smaller halo it starts infalling and merging into the larger halo, because it typically brings a galaxy in with it. Okay, so these galaxies that are brought in are called satellite galaxies, and they tend to be more numerous in larger mass halos. So now we're seeing an increasing number of galaxies and an increasingly massive galaxies also at higher halo masses. And we can even go a little bit further. We can try to predict other galaxy properties that are observable too, such as the rate that they're forming new stars, which affects their color. So now I've added colors and made some of the galaxies red and some of them blue. Galaxies with ongoing star formation tend to be bright blue, like our own galaxy, the Milky Way, which is pretty blue. The quiescent galaxies, on the other hand, tend to be more red in color. And at very high masses, both in halo and galaxy mass, and sometimes at low masses too, a little bit, it's more likely for these galaxies to be red and quiescent. But it's right in the middle. There's the sweet spot where I try to make it a little bit more likely for galaxies to be blue and rapidly forming new stars. So I made the galaxies in the middle, yeah, a little bit more efficient at this process. Now, when we compare this theoretical picture to observations, though, we have to account for the fact that not all of these galaxies are able to be seen in our sample, in our observational sample. Some of them are going to be too dim to see with our telescope, for example. So we have to throw out the little guys on the left and the little satellites by applying a selection function. So now some of them are gone. Okay, so now we have halos on the left that are too small to host a galaxy in our sample, and halos on the right, which all host at least one galaxy. And in the middle, it's kind of 50-50 whether or not it hosts a galaxy or not. And that's just for central galaxies. For satellites, it's even arguably a stronger function, I guess, of halo mass, the occupation of the satellite galaxies, because you can see all the way at the left, there's no satellite galaxies at all, and on the right, there are a ton. So if we know all of this, what am I even doing here? Well, my hypothesis is that galaxy formation depends not only on the mass of the halo alone. I think we can draw secondary correlations with other halo properties. For example, well, in general, this is a phenomenon or effect that when we study it, we call it galaxy assembly bias, which is still somewhat a contentious subject in the literature right now. But if galaxy bias exists, then it could potentially cause systematic errors and bias the things that we infer about cosmology through galaxy surveys. So in this example cartoon, I'm trying to demonstrate that there's probably this one. I think we expect there to be this correlation between star formation rate and the accretion rate, which is just how fast is the halo sucking in material from around it. And that material can possibly be used as the fuel for star formation. So there's some physical motivation behind this correlation here. And you'll notice I've made some of the galaxies up on the top, more likely to be blue, and the ones on the bottom a little bit more likely to be red. I don't know. I just did it very roughly though. Cool. So now we've walked through the whole galaxy halo connection as a cartoon. Unfortunately, we can't just show a cartoon like that to computers and say go. Instead, we use mathematical functions, and these describe the expected occupation of halos, just in the same way that I described to you in the cartoon, essentially. But all you need to take from these equations and the slide in general, I guess, is that we call this type of a model a halo occupation distribution model, or HOD. So to fit this kind of model, we need a couple of observables. Firstly, we need to make sure that the abundance of galaxies in a survey matches the number of halos in the simulation that we're putting them into. For example, in simulations, we see a lot of really small halos, and similarly in observations, we see lots of small galaxies if your selection function is fair. And on the other hand, large mass things are rare in both cases. So in fact, we can actually partially just constrain the galaxy halo connection from this alone, but there are also other metrics we can use, other ways to make sure that the galaxies that we think go in the halos really do fit in them just right. So yeah, the other main way that main thing people use is quantifying the clustering signal. Just that spatial distribution, the thing that looks like the cosmic web that you saw earlier. But what we do is we use a statistic called the 2-point correlation function, which I call WP, it's on the y-axis. This quantifies the excess probability of finding a pair of 2 points that are a given separation apart. And the separation distance is RP, that's what's on the x-axis. To give you a rough idea of how this works, I just plotted a bunch of totally randomly distributed data on that plot, or on that picture on the left. And occasionally with random data, you have points that are just happen to be close by chance, but we don't call that clustering. This is our 0 point. This is 0 correlation. And theoretically, if you had a perfectly random distribution, your 2-point correlation function would be 0 at all separation scales. Next, I'll show you data with a little bit of clustering. So here's data from a simulation where I just selected very low mass halos. And you can see they preferentially live nearby other halos, which is why the WP is larger at lower separation scales. There's a larger correlation there. Next, here's the population of medium mass halos. So these ones tend to be less likely to be sitting around in really underdense regions, and they're more likely to live in clusters with other halos. So they're even more clustered together, actually, at all scales. And we're starting to see a trend where more massive halos are more clustered. This trend continues when we go to very high mass. So these really high mass halos only live in the densest environments, which means they have the highest clustering signal. I could show you exactly the same thing if I swapped the halos with galaxies, where low mass are the lowest clustering, high mass are the highest clustering. If I did it just right, then the clustering signals should look roughly equivalent. So in conjunction with number density, the 2-point correlation function make sure that we get this connection between galaxies and halos much better. All right, so finally, here are some past observational constraints of the 2 main metrics I just talked about. Number density, in this case, as a function of different halo masses, which is just the abundance, how many do you expect? And the 2-point correlation function, as measured in SDSS, the Sloan Digital Sky Survey. So these are the 2 main observables people use, but you can actually further improve these by using more metrics. In fact, to uniquely characterize the spatial distribution of points, you need to measure every endpoint function. So I've shown you the 2-point function, but then you would need to measure the 3-point function, 4-point function, and so on. But it's hard to compute all of that. So there's this one particular metric that does a good job of summarizing all of this information into one easy to understand statistic, and it's known as counts and cylinders. All this is a probability distribution, this plot down there, which tells you the chance that a probability or that a galaxy has to host a certain number of neighbors, where a neighbor is defined as being within a given boundary from it, and the shape of our boundary in this case is a cylinder, hence the name counts and cylinders. And the cylinder is always oriented along our line of sight because we have less information about the redshift distance position. So later on, I'm going to show you that if you measure this this statistic, or even just several of its moments, like the mean, standard deviation, skewness, and kurtosis, you can add a lot of extra constraining power to your analysis. So this is my last background slide, it looks like. So hopefully everyone followed that 100%. Just kidding. Actually, so if there are any quick questions on the background, particularly from non-astronomers, it's probably a good time to ask them.
Also a very, very, very astute body.
They are. Yeah.
Would a halo also be described as porous?
No. So a torus. Okay, so yeah, that's something maybe I should have described a little better. A halo is actually a misnomer for the shape of what we call a halo. It's real. A halo is spherically symmetric and it's densest in the middle, whereas a torus is actually like a ring structure, right? There's nothing in the middle of the torus. A halo, the further you get to the middle, it's really just it's a clump of matter and approximately a circle or a sphere. Yeah, great question. Malcolm? Yeah, it definitely changes the constraints you get a little bit, and it changes what you're sensitive to a little bit. If you're too sensitive to the redshift dimension, it just gives you slightly different information. And from like some testing that not I did, but a past graduate student did, they showed that this is like a really great metric for constraining the galaxy halo connection and assembly bias in particular. Yeah. Good question.
Hey, Alan.
Yeah.
This is Caleb. Is there a way you can validate the results of your HOD model in the future?
Let's see. Who asked this? I can't see. Caleb. Let's see. Yeah, I mean, as more data comes in, you can just kind of continuously keep validating it. I guess additionally, as simulations keep improving more and more, eventually we'll probably learn more from those, and that can help validate it. Although I would kind of expect that this empirical way of thinking about things is probably always going to be what informs simulations, not vice versa, just because of how computationally difficult it is. But yeah, I mean, the assumption on its own that galaxies have to form in halos, for example, kind of has to be true from what we can simulate, kind of, or approximate. We know for sure the large scale distribution of matter, so we know galaxies have to form inside of halos. I'll say that. So we're pretty confident about that. But I mean, good question. Yeah.
Can I ask you a question to follow up on Newman's question?
Okay. Oh boy.
Hopefully it'll help you. I think you know the answer. But I think it'll help you. Why do astronomers always use cylinders and not spheres? Not always, but typically use cylinders.
So like the historical reason, would you
Or
say?
even practical.
So I think I hinted at this a little bit, but the line of sight distance that we measure to a galaxy is fairly uncertain. We measure the distance through the shifting of its light, which comes from the expansion of space since a certain look back time. And that's well, there can be a little bit of uncertainty in that, although if you're using spectroscopic data, you can nail that down pretty well. Really, where most of the error is coming from now is there could be peculiar velocity, which would create a Doppler shift in the spectrum. And that's fully degenerate. You can't separate that or distinguish what the velocity is in comparison to the distance. So you just assume all of it is to the distance and there's some plus or minus velocity factor. And that's kind of why that distance is the most uncertain here. Is that kind of what you're getting at?
Yeah, basically.
Okay,
So you
cool.
in astronomy, you use cylinders, but you measure the circle as just where it is in the sky. Remember that?
Yes. Yeah.
At the depth, you don't really know that well.
Right.
So you choose a shape that's pretty deep, but like even if you make a mistake in the depth, it doesn't matter.
Exactly.
Basically.
Yeah. I should definitely say that the circle is a much smaller region. Yeah, exactly what Andrew just said. We can measure exactly where a galaxy is on the sky, and that's what this dimension is showing. Where on the sky is the galaxy. Yeah, great questions. Any other quick questions? Yeah, if not, I'll get into my first thesis project. So I've been talking about how you can measure several of these observables, namely the stellar mass function, 2-point correlation function, and counts of cylinders. These are all measured pretty well in the local universe, but as you push to more distant, higher redshift samples, we need a lot more spectroscopic galaxy data. And that's basically, that means that we need to measure the amount of light that it outputs at very fine intervals of wavelength. And actually, we're expecting to get a lot more of this spectroscopic data soon. For example, this is PFS, the instrument up there, prime focus spectrograph. Starting next year, fingers crossed, it's going to measure the spectra of thousands of galaxies at a time in an upcoming high redshift galaxy survey, which is going to be using the Subaru telescope on Mauna Kea. And I'm going to look at this survey and a couple others, like the Waves Deep survey and the Moonrise survey, which are similar programs. They'll give us similar data to PFS, but at slightly different look-back times. And in preparation for these surveys, I've roughly quantified their combined power of constraining the galaxy halo connection at various epochs over the history of the universe, kind of to see if it's changed. And I've shown how this constraining power is affected by several survey parameters, like how much sky area is the survey surveying, and target density. So now I'll quickly talk about how I made mock galaxy catalogs that contain all of the necessary information to answer this question. And I started with what's probably the best empirical model that currently exists, the universe machine. I think the astronomers in the room know I could talk about how universe machine works for hours, but I'll try to keep it brief by saying that it's a sophisticated galaxy halo connection model that can produce reasonable galaxy populations over the entire history of the universe, which is really impressive. However, it describes galaxies by their fundamental properties, like their mass and their star formation rate. So conducting mock observations requires making some good assumptions about the light output and the color of these galaxies. So how do we go about predicting the amount of light emitted by a galaxy? I guess this is requires a little bit more background about how light output in galaxies works. Most of the light in galaxies comes from stars. So the amount of light emitted by a galaxy is kind of roughly corresponding to the amount of mass or the number of stars in that galaxy. But not all stars are equal. Blue stars, for example, tend to be extremely bright, especially on the blueward side of the optical light in the galaxy spectrum. And so they just tend to be brighter for their mass. For example, this, let's see. I forgot to say that the blue stars actually have very short lifetimes, though. So you can only see these really, really bright stars if there's ongoing star formation in that galaxy, or very recent, but basically ongoing. And for example, this blue star forming spiral galaxy on the left of this plot is ongoingly forming new stars, and so it looks brighter and bluer. Quiescent galaxies tend to look a little bit more like the picture on the right. Not as much going on in that picture. And so let's see, if basically if you imagine that these galaxies have the same stellar mass, which is not true at all, but let's imagine, then the one on the left, the bright blue galaxy, would be emitting a lot more light for its given stellar mass. And so if you know basically the color of the galaxy, then you can calibrate this mapping between the mass and the amount of light emitted. And we call this a mass to light ratio. And so you can see the blue galaxies on the left have the lower mass to light ratio. Like you get their light converted over to mass as a lower mass than what you would expect if you used a flat trend. Then I used this basic principle to calibrate the empirical properties into the universe machine. And I trained this on a galaxy sample here from Ultra Vista, which is a survey that goes to around similar redshifts as samples I'm trying to mock. So using that principle, like I said, and a few other calibration steps, see the whole thing, I developed this full machine learning procedure to assign the amount of light that we would observe from each mock galaxy in universe machine. And most importantly, I gave it an acronym climber. So yeah, this procedure has allowed me to create the mocks that are currently being used by the PFS collaboration primarily, to quantify the scientific abilities of their program that's starting soon. And this is just a visualization of that mock, and some of the data that you could measure, like mock measurements of each galaxy. These are types of spectra, for example. Okay, so using those mock catalogs, I was interested in testing measurements of the 2-point correlation function, because that's how we constrain the galaxy halo connection. And that's what I'm interested in improving our scientific output of. So I conducted mock surveys of each of the programs that I mentioned previously. And this plot just shows the relative sky area. Some of them are larger on the sky than others. And I've also applied their brightness limits and the average targeting density, which can miss out on some of the galaxies basically due to collisions between the fiber arms that are observing the galaxies. And here are the observables that we get for each of these 3 samples. The number density versus stellar mass is on the left, and then the 2-point correlation function clustering measurements are on the right there. And to quantify the performance of how good we're measuring these observables, I needed to calculate very precise uncertainty measurements. So these error bars, the gray bands, come from 600 bootstrap realizations of my mock catalogs, just looking at kind of different volumes in the simulation, essentially. And this is the best way to account for all of the sources of uncertainty in a survey simultaneously. So doing all of that, I made this plot to demonstrate a main takeaway that I got from doing these mock measurements. It shows how the correlation function uncertainty is dependent on a few of the related survey parameters, like the survey area and the targeting density. So here I'm showing 2 likely ways of varying such parameters. On the top, I'm showing how you can increase the survey area and even hold the number of galaxies constant, and you'll substantially improve the constraints that you'll get on the 2-point correlation function, even at the cost of having less densely sampled data. In the bottom, I showed that you can actually increase the sample size, but if you keep the volume of the survey the same, for this example, you're going to get very little improvement. And this is due to a source of uncertainty that we call cosmic variance, which is basically the idea that if you look at one patch of the sky and look at another patch of the sky, they could be drastically different from each other unless if the patch of the sky is sufficiently large to incorporate a large enough sample. So yeah, that's cosmic variance. And the main takeaway here is that PFS is probably cosmic variance limited. And I would like, at least for my scientific goals, for future extensions of surveys like PFS to prioritize increasing their survey area before circling back and improving their target density, basically. All right, so now my second thesis project I'd like to share about is a galaxy halo connection study, this time of real data, which is aided by the statistic I mentioned, counts in cylinders. So in the study, I looked at some of the first data from the dark energy spectroscopic instrument, aka DESI. Similar to PFS, waves and moons, DESI is a multi-object spectrograph, which means it's observing thousands of galaxy spectra simultaneously at any given time. This is a picture of the instrument and a zoom in of the individual spectroscopic fibers. These are the things actually measuring the light and then feeding them to a spot where they disperse the light, and you can see the whole spectra. By the way, I'm using data here in this talk from the DESI early data release, which was only just publicly released about 2 weeks ago. So this is a very early look at what DESI can do as it continues to collect data over the next several years. That's a good question. Probably several feet, I imagine, wide, right? It's like 1 arm length.
Well, the circle is, I think it's 1.5 meters.
1.5 meters. Okay. Yeah.
5 feet.
Yep. 5 feet.
What about the zoom?
Then the zoom in, well, you can see the box, so that's good. Yeah, inches.
Yeah, about 1 meter.
So one of the programs of the early data release of DESI was aimed at obtaining very high spatial completeness within 20 regions of the sky that are plotted on the left. And this data is called the Survey Validation 3 sample, or SV3. So this high spatial completeness is what allows us to make reliable measurements of the counts in cylinders, because you can measure the number of neighbors around each galaxy fairly reliably. And we only have to throw out on the right plot the galaxies which lie really close to the edge of the boundary, basically. And so it's these points in orange that we had to throw out the cylinders that are centered around those galaxies, because we can't reliably measure the number of neighbors that they have. But we can keep most of it. Everything in blue we can keep. So that's pretty cool. And SV3 actually conducted several surveys of different types of galaxies, or tracers as they call them. But I'm focusing on one which is an R-band apparent brightness limited sample called the Bright Galaxy Survey, or BGS. So here's what the BGS sample looks like if you plot their intrinsic brightness, aka absolute magnitude on the y-axis, versus redshift. And since redshift is a measure of distance, objects that have higher redshift tend to also have higher intrinsic brightness, because if they weren't brighter, then we wouldn't be able to see them further away, basically. And these colored boxes that I have here show different redshift cuts and magnitude thresholds in order to make well-defined fair samples to study the galaxy halo connection of. And for each of these 4 samples, I measured the 3 summary statistics that I've been talking about this whole time. As always, I measured number density and the 2-point correlation function. But the SV3 data set really isn't optimized, I would say, for these statistics. These are generally better for large volume surveys, as I concluded from my last project. And they don't benefit a ton. They benefit a little bit, but not a ton from the high targeting density of SV3. That's a big part of why counts in cylinders is my 3rd summary statistic, because it's well, it's aided by that high density, and it's really helpful at quantifying the galaxy clustering signal in this data set. All right, so now to motivate the need for me to develop the pre-tabulation algorithm, GalTab, I want to briefly explain how, like the computational method of how we actually infer the halo occupation distribution parameters that produce the best fit to those summary statistics that I just showed. I've used a method called Markov Chain Monte Carlo, or MCMC. And this is the standard procedure to do something like this type of problem. And basically all MCMC does is it guesses a set of model parameters, and then it executes a function to measure all of the summary statistics. And it iteratively compares between these different predictions in a way to see which predictions, which correlate to which set of parameters, are most consistent with the data that we see. And so it ideally outputs something that looks like this, I guess. This is a 7-dimensional probability distribution of model parameters, of 7 different model parameters. And you can visualize this 7-dimensional distribution by just looking at 2-dimensional probability distributions, slices of the 7-dimensional PDF. And this is how we can kind of see by eye like what combinations of parameters produce the best fits. So with this method, the number of iterations to converge on this kind of a PDF, it can vary drastically. And a key thing that can hang up your fits is a stochastic prediction function of your observables. So that is if there's any element of randomness, where the same model parameter choices, if you keep sampling over and over, it can produce slightly different results. This stochasticity it slows you down, and so that's therefore the main thing I'm trying to minimize with my pre-tabulation algorithm, which I'll get into now. I've called this algorithm GalTab because of the way that it pre-tabulates galaxies inside of each halo before it actually knows how many galaxies they should be. And tabulating all of the placeholder galaxies is just one step of the algorithm, but it's not trivial. So we have to be careful about the number of satellite placeholders we tabulate. And in this example, I've drawn all of the satellite placeholders in blue, and for this example, let's assume there are 6 satellite placeholders in the halo. So the goal is to approximate the standard HOD assumption that the satellite occupation distribution is Poissonian. But it turns out that if you have a finite number of things that you're drawing independently from, this is a binomial distribution. Fortunately, the binomial distribution converges well to a Poissonian in a certain limit. The approximation that we need to work out is that the p-value, which is the probability that one of these placeholders actually hosts a real galaxy, has to be less than about 0.05, so about 1/20. Therefore, in our decision to populate how many satellite galaxies, we take some fiducial model, calculate the expected number of satellites around each halo, and multiply that by 20, and then round up and to the nearest integer, and that's how we calculate that, our number of placeholders. Step 2 is the algorithm that actually, well, so this is computationally expensive, but it's pretty straightforward, I think. You draw a cylinder around every single galaxy, and you just look at how many neighbors, how many placeholder neighbors it has, and then you tabulate a list of all pairs of things that are neighbors with each other. Then you store that in a very large table. Finally, step 3 is a function which predicts counts and cylinders in a deterministic way, and it's fast, which is important because even though we're reducing the number of times we have to call this by being deterministic, we still have to do it many, many times. So there's a ton of math behind step 3. I'll spare you most of that, but what I will say is that the population counts and cylinders distribution here is a superposition of the distribution PDF of the number of neighbors in an individual cylinder. So if you take this cylinder, which has some finite probability of there being any integer between 0 and 6, hopefully a small chance of being 6, if it's a good approximation, then you just add up all of those individual PDFs, and you get to this whole population counts and cylinders distribution. Yeah, so that's how the pre-tabulation algorithm works. Okay, so the black contours on both of these plots here represents the same thing here. These are my best final constraints on assembly bias, which is my main parameter of interest in the study. In these plots here, though, I'm contrasting the results we would have gotten if we used different methods, because I'm trying to justify that the methods that I used, that I developed, are helping us. So the figure on the left is a proof of concept that my Galtab algorithm helps the MCMC convergence, because the orange contours come from the same number of MCMC iterations as the black ones, but the orange curve used the standard counts and cylinders methods from the Halo Tools package, which Andrew Heron developed. My method produces a much smoother posterior because it's already well converged with the same number of iterations. And the figure on the right shows the importance of including counts and cylinders in the analysis at all. The blue curve here is what you would get if you didn't use counts and cylinders as a constraining statistic at all. And this results in significantly less powerful constraints than you get from our true results, the black curve. And this is why we put so much effort into including counts and cylinders in our set of summary statistics at all. So now, just looking at the two of the samples, not all 4, to make it easier to look at, here's sort of what the fits to our summary statistics look like. The solid lines are the actual best fits. The dashed lines are the best fits we'd be able to achieve without assembly bias. First of all, the brightest sample really shows no evidence for assembly bias, and you can see that pretty clearly that the dashed line doesn't improve the fit at all. While it does actually substantially improve the fit for the blue sample. And I guess a bit of a caveat here is that it's pretty clear the HOD model we're using isn't achieving a perfect fit to the data. There's definitely a little under prediction. But I will say that these errors are only, I guess, slightly beyond the error bars. Everything is within 2 sigma. So it's statistically possible that the model is correct and the data measurements are just a bit off. But I think we should be a bit skeptical of that. And I'm definitely seriously considering the possibility that the data model mismatch is real. And I'll mention this a bit more later, but I'm starting to explore ways that we can resolve this by introducing new degrees of freedom into the HOD. And finally, combining all 4 of the magnitude samples that I defined at the beginning, we get a pretty good holistic picture of how the galaxy halo connection is dependent on the brightness of our galaxy samples. So the top panel shows the expected halo mass for a given central galaxy of a given brightness. On the x-axis is the same for all of these. It's just the brightness of the galaxies that you're looking at, where the brightest is on the right. And the middle panel shows you the halo mass that you need to host at least one satellite galaxy. I've also shown the dashed line that shows you the expected halo mass to host two galaxies to kind of show you how that occupation function scales, where you get more at higher halo masses. But the biggest deal here in this result is the bottom panel. This is our assembly bias measurement. And although we don't find any assembly bias in the satellite galaxies really at all, there's definitely a positive correlation, a positive assembly bias signal in most of the central galaxy samples, basically just with the brightest sample of the low redshift sample excluded from that statement. And so this means that there's almost definitely a positive correlation between the concentration of a given halo and the luminosity of the galaxy that formed inside of it. And this, assuming this is right, this probably has pretty big implications for the physical processes that drive galaxy formation. This could point to some bias, potentially, in cosmological analyses that didn't incorporate assembly bias. So just to briefly recap the accomplishments of both of these projects in my thesis, I constructed the Climber mock galaxy catalogs. I tested the 2-point correlation function measurements of the upcoming PFS survey and determined that it is cosmic variance limited. I developed and implemented GalTab for rapid Canton cylinders predictions deterministically from HOD models. And I found one of the most significant signals to date of galaxy assembly bias. And looking ahead, I've identified some of the key questions that I'd like to address both in the near future and as I continue my research career at Argonne National Lab, where I'll be starting as a postdoc this fall. First of all, there's a suspicious level of model data mismatch in my DESI analysis. So in the short term, I'm going to start thinking of ways to make the HOD a bit more flexible. And yeah, if you haven't noticed yet, I really enjoy developing methods that address computational problems in the field. So I'm excited to start contributing to an effort at Argonne where they're developing a tool called the Differentiable Stellar Population Synthesis, or DSPS. And this is a really cool program that could make it way faster to infer the star formation history on the left of a galaxy given its spectra, which is on the right. And you could even potentially connect the star formation history to the assembly history of its halo, which is really cool as someone who studies the galaxy halo connection. And with that, I just want to thank everyone again for coming and listening to me. I'll open the floor for questions.
All right, so now we have questions from the general audience, not the thesis committee evaluated. And Alan, I'll ask you to remember to try to repeat the question so people on Zoom can hear.
Oh yeah, I think I forgot that earlier.
That's okay. So now's your time to fire away. What do you want to know?
On your final assembly bias, on the most massive sample had the weakest assembly bias signal.
Yeah. Mm-hmm.
So is there a physical reason that you would expect that to be the case? Or I also missed the error bar on that.
The physical reason I think is a little hard to be very confident of in such an empirical
I thought you were going to repeat the question.
Oh, sorry. The question was in the highest mass sample, there is no assembly bias detection signature. Is there a physical reason for this? Saying it's hard to really get to the bottom from it from an empirical model alone without performing basically simulations and seeing which ones produce the best fit. I kind of get the feeling that this is the sample that's like the least actively forming new stars. And so if assembly bias is somehow related to like star formation rate specifically, that's driving the correlation between additional halo properties and the assembly history of the halo, then the ones that are least actively forming stars might have the lowest correlation. I mean, that's the best thing I've got to that, but that's definitely a very difficult question and a good question. Yeah. Malcolm?
I know your presentation, like you showed your paper being the one that not there. one that's down and say it's like 5, and are they like 10,000 points? Are they 10,000 points?
Let's see. If you take like, oh yeah, so the question is how large are the simulation volumes that I use to simulate halos and then to constrain the HOD. So the number of data points of particles that are being simulated through gravity is something on the order of, I guess, 10 to the 9 or 10 to, I think 10 to the 10, roughly for these galaxies. So a lot. Yeah, and you get then millions of halos out of that. You get the physical scale of these simulations, specifically the ones I'm using, are 400 megaparsecs divided by 0.7, I guess, so 500 something megaparsecs on a side. So then 400 cubed would be your volume, and I don't know how to describe how large a megaparsec is to you, but it's a million parsecs, which is roughly the distance from your star.
Parsec's 3 light years. So
Yeah.
it's about 3 million light years.
So are you doing all this in simulation? Or are you doing
The simulations themselves, I don't have to do, fortunately. The output data from them are publicly available, the ones that I'm using. Yeah, but they are performed on supercomputers, yes.
specialized program highlighting it?
Oh yeah, lots and lots of computational tricks to make it work.
Could you go back to slide 47?
I think I can go to that directly.
It's always good when somebody begins with, go to this particular slide.
All right.
I'm a bit confused what you mean by satellite connection here.
Okay. Satellite fraction. Yeah, I didn't talk about this at all. Almost unrelated. Maybe I shouldn't have it. But I mean, it's a good thing. I think to kind of it's a cool thing for me to explain. So I'll just say that the satellite fraction is if you take all of your galaxies at that stellar mass, say on the x-axis, you're still looking at a slice, very small region of stellar mass. It's just what is the fraction of the galaxies that are satellite galaxies versus central galaxies, because there are two main types of galaxies that I'm modeling in the HOD, and that's centrals, which are located at the central of the halo. That's like what formed in that halo. It's always formed in it. Maybe things have merged and stuff, but that's primarily what's formed directly from that. And the satellite galaxies are what have infalled through other halos over time. Yeah, great question.
Laura. Thank you so much for a fantastic talk. My question has to do with something uniquely brought up with the end, which is DSPS.
Yeah.
And you said you're excited about studying the connection between star formation histories and assembly histories of the halos in the galaxy. Can you speak a little bit about what that would entail and what the
there is a lot of room for me to still decide exactly what that looks like, I would say, but yeah, I definitely want to look into some of the parameters. So the question was, sorry, I always remember it halfway through. Gaurav told me that I did a very nice talk, most important. And that was all. And he asked exactly how is the modeling done for connecting the star formation history to the assembly history of the halo, and what do I want to get out of that? What do I want to learn from that? So I think there is a this is gonna get technical, I think, but they model the star formation history as essentially the accretion rate of a halo as driving as the fuel of the star formation, like fundamentally. So, and then there's this efficiency rate for based on how massive the halo, how many feedback processes you expect to be existing for how efficient you expect all of that accretion of matter to turn into star formation at every step of the history. So I think probably the most interesting thing, or I mean, there's a lot that you could potentially learn from this. I mean, every step of the way is interesting. How strong is the correlation between the rate of the accretion, exactly what halos are most efficient, better constrain like what that function looks like. The functional form of star formation history can tell us a lot about what things are driving the feedback between the accretion of stars and then what's actually produced. So yeah, there are a lot of potential directions. I don't have like exactly a perfect answer yet, I don't think. Yeah.
How come we get, all right, there we go.
And so you've got the real line in the back of the thing, and you don't match up with the movie for the big side, right?
Yeah.
And so, do you have any idea of the Bible match? You said about that, but is there any specifically you would buy, like, something wrong here?
That's why I should.
So the question, which was a very difficult question, I think, is like you see on this slide that the data in the top plots, particularly in the middle panel with the 2-point correlation function, are under predicting. And a lot of that, I guess, first of all, is driven by the fact that we're trying to simultaneously fit the 2-point correlation function and Canton cylinders at the same time. And so this isn't, a technique that there's a ton of history on. I mean, there's some, but it's most people don't choose to fit both of them simultaneously. And it could be that like we're just having a really hard time with either our cosmological models or with our probably more likely somewhere on the galaxy halo connection side, where if we tune it so that we get the number of counts and cylinders just right, you're not able to do that simultaneously, right? And the primary way that I'm looking into addressing this is by changing the actual like functional forms of so I mean I won't go back to the slide exactly, but basically there's a function that tells us the expected number of galaxies according to the halo mass. And from what I've kind of observed from simulated examples like the universe machine, that function does not really look exactly like the function that we assume in the HOD. The HOD is expected to be like this very symmetric function that like starts at 0 centrals, goes up very smoothly to 1, but in reality that can be very skewed and particularly more like random on the higher mass end, it seems like. And so I think one thing that I would at least test to try to figure out to address what could fix this is by changing that and allowing a skewness in that scatter between halo mass and galaxy mass. Yeah. You have another question, Malcolm?
Yeah, before you ask your question, I'm gonna take the chair's prerogative, and I'm gonna ask a follow-up question.
Oh boy.
With the early DESI data, how statistically significant is that?
So the statistical significance is under 2 sigma, almost 2 sigma. So what that means is there's at least a 5% chance that we could produce this type of a data, assuming that our model is correct. So it's not even like definite that there is a mismatch. It could just be a statistical fluctuation, but unlikely at the almost 5% level.
The data will get better.
Exactly. Yeah.
One of the reason I'm bringing that up is because when you look at these plots, all the points are correlated. So it's not, you can't just look at each point on the graph and say, oh, there's a million points that all disagree. More like only 1 or 2 points, because they're all strongly correlated with one another.
Yeah. Yeah, what Andrew's pointing out here is that when you look at the middle panel in the 2-point correlation function, what I've actually technically plotted is, I think, 13 individual points that I've connected with a line and with a band. But all of those are not individual data points technically because they're highly correlated with one another. And when you move one, the other one tends to move with it. And that's actually a reason why the red sample is such a bad fit, because even though the bottom point goes up to try to fit the low scale clustering, I think there's according to the covariance matrix, that's not a very likely shape for the low scale 2-point correlation function, apparently. I don't know. For some reason, the red curve is showing up as a worse fit as a blue fit. That's all I'll say.
We give you one more, Malcolm, and then before we leave, we're gonna make sure we get a question from somebody who's not had kids. All right, go for it.
That was part of the justification. Yes. Did I call it climber because I like climbing? Yes.
What fraction of time did you spend working on the science versus thinking of the acronym?
What fraction of the time did I spend doing science versus thinking of acronyms? Ooh. There was like definitely a solid like day or two that it probably was iterating because like I had several research groups thinking of a name for it, I think at one point. And I'm not sure if climber was thrown out by Rachel Bezanson's group. I think it may have been a product of that group meeting, maybe. I don't know.
All right, we have a question from any question, anyone, could be anything. It's your one chance. If you've ever wanted to embarrass Alan.
Hey, Alan.
Yeah. Who's speaking?
Yeah, Caleb here again.
Yeah.
Can you just elaborate a little bit more on your GalTab library you developed for this project?
I could elaborate a ton on it. So let me see. I'll just go back to, oh, I missed it. I'll just go back to this slide. Is there any particular part that you are interested in hearing more about?
Really just like a quick TLDR. I went to your GitHub page and I didn't see much extra documentation outside of
he caught
setting
me
it up.
on the low document. That's the documentation is I would say work in progress, but it's actually something that I'm planning to be a work in progress soon. Yeah, the documentation doesn't really exist super well yet. Just descriptions of how to download it. So the TLDR is that this algorithm is able to predict the summary statistics that you saw here. And it's able to do it in a way that if you give the same model parameter several times, it will always produce the same result. This is in contrast to typical modeling techniques, which are, well, we have the expected number of galaxies per halo, and that's going to be like, I don't know, 2.3, and then you draw from some distribution to calculate the actual number of galaxies, and that's going to be different each time, and then you're going to get different clustering measurements, just different statistics of that sample every time you model that. So this is a way of modeling the actual expected distribution of a full population given this model. I'd say that's what the core idea of this is, and the way that we do it is just by populating placeholders and saying that these placeholders are the only places in the universe that galaxies can exist.
Thank you.
Mm-hmm.
Any other questions?
Alan, I had a question if that's okay.
All right, who is this now?
Theoki.
Okay, cool.
You might have mentioned this already, but I was curious, once all of the DESI data is complete after the survey is finished, which of your summary statistics do you think is going to benefit the most from it in terms of providing the strongest constraints?
Oh, I mean, I have an extra slide for this. Yeah, I didn't think I was going to get such a technical question. Wow. Oh, I didn't know. Yeah. I mean, I guess Yoki has probably seen this plot. Where is it? Here? Yeah, so these are, I'm not gonna explain super exactly how it works. It's a machine learning method of figuring out how important different predictors are for predicting a given target statistic. But this is a measure of how important all of those predictors are. For measuring, we have 6 different target statistics. Those target things that we're trying to predict are model parameters, like the things that inform us on what the galaxy-halo connection are. The things in the top row are related to predicting how many central galaxies per halo. The thing in the bottom row are for predicting how many satellite galaxies per dark matter halo. And I've split it into number density on the left, which is separated by a dashed line. Then we have the 2-point correlation function in different bins, and then the Counts cylinder. Not in different bins, but in different moments. So mean is the first moment, standard deviation, skewness, kurtosis, etc. I wouldn't, so I mean, the most important statistic is pretty much always number density. I don't think you can get away from that. You need to be able to predict the number of galaxies from your model. And then eventually, when the full DESI data comes out, the thing that's going to really, really improve, well, is both the number density and it's the 2-point correlation function, because the 2-point correlation function doesn't really care all that much if you have data that isn't perfectly sampled. If you have fiber collisions and stuff, that'll be okay. We'll be able to keep adding more data on top of our 2-point correlation function data. And so that's going to drastically probably become more important for everything. Right now, it's actually almost one of the worst predictors, I would say. And maybe that's why the fit like least prioritized fitting 2-point correlation function well, potentially, just because it has large uncertainties, right? And Counts and cylinders is going to improve probably less. I'm not sure exactly. We'll have to do like a lot of tests to make sure that our results are valid, basically, mock tests, if we want to increase the number of data we use for Counts and cylinders. But I would say right now, at least for measuring like the satellite parameters of the HOD, we're getting a lot of information. If you look at like assembly bias for satellites, the alpha, which is the slope of the satellite occupation function, you're really, the Counts and cylinders, the first 3 moments at least, are very, very important for alpha. And quite a few of these observables, kind of a surprising number of these. Does that answer your question?
Yes, thank you.
Probably talked about that for too long.
Any last questions? Everybody said everything they want to say. Oh, there we go. All right.
So you'll be at R9, and more like SE able to continue to get more info and get other simulations and stuff, giving out more information. Are you most likely, will this kind of turn into a side project with the lawyer are doing, or will this continue to be a main focus? It's probably time intensive for you to keep working on this.
Yeah, I think it's very likely that I or another grad student, maybe in the future, that I could help out with a similar project to recreate kind of similar analyses that I did with this sample, just apply it to the larger sample as a whole. That's something that will happen. It's not something that I have planned, and it's kind of a long ways in the future at this point anyways. But yeah, I mean, it's a canned, ready to go science project. And the question, by the way, sorry, was basically when the full DESI data comes out, do I have plans to rerun all this whole analysis with the future data? And the answer is kind of. Not. I personally didn't use supercomputers. I don't know what you would call Osiris, but it's a cluster that is owned by several professors here. One of them is Andrew, and it's a cluster that has several nodes. So in a way, it's similar to a supercomputer, but not at as large of a scale. It's just kind of a nice thing that I can run all of my analyses on and forget about it, and it doesn't slow down my laptop. Well,
Okay, not so.
yeah. I mean, at some point, it would have been considered a supercomputer, right? Maybe. Well, before it existed, maybe. But I don't know when it came to be.
Last call. Any questions?
It was a very funny joke.
All right. Take out the question. We have another one.
So a science question.
All right.
Now that your PhD is almost over, what's the most thing that you like? What's the
Okay, this is the hardest question that I've gotten. What is the hardest, or what is the thing that now that I finished my PhD, almost, fingers crossed. All right, yeah, I spoke too soon. What was the thing that I enjoyed the most?
Two demerits.
What was the thing I enjoyed the least? Let's see. I mean, the thing I enjoyed the most was probably all the people. It's really great company. I enjoyed just getting to know my fellow grad students, postdocs recently, and professors. Yes, both of you, the two postdocs. Yeah, it's been really great. I really feel like I've been supported a lot by all three of my professors, and I feel really lucky for that. The hardest thing was the core classes for the first couple of years, and it's just kind of getting sucked into that and feeling lost for the beginning of my grad school career. But that quickly turned around.
But Alan, you were a
honestly,
star of the core courses, I can tell you.
well, that's a huge compliment. Thank you, Joe. Yeah, I took 4 semesters of quantum mechanics. And my last 2 were with Joe Boudreau, and apparently I did well in his class. Yeah, I mean, I think kind of going through all the core courses and then trying to start research and like kind of having that disconnect between doing research as an undergrad and not doing any research for a while kind of got me lost for like what I wanted to do. That definitely very quickly turned around. Yeah, I think it was all a very positive experience, and I enjoyed my time here.
All right. In that case, let's thank Alan again. So the next step is going to be the questioning of Alan by the committee. Which I'm going to call for today the revenge of the people born before 1995. We will toast Alan after we are done. Usually takes about half an hour.